Okay, in this chapter we'll look at applications of the three Newton's laws. We'll apply these three Newton's laws and solve problems in various situations. Now Newton's first law says when no force acts on an object, its velocity is constant, that is, its acceleration is zero. This is really a special case of Newton's second law. When force is zero, acceleration is zero. That's when this is zero, acceleration is zero. And acceleration zero implies v is zero or v is constant. Well, it implies v is constant, and so if v is zero, it'll remain zero. Okay, let me redo that. So that implies v is constant, and so v can be either zero or a non-zero value, but v will not change. So that's Newton's first law. Again, so here's a real life example. You've all played air hockey, and you get the puck moving and it'll maintain its velocity till it encounters a force. Okay. So here's Newton's second law. Newton's second law is a statement about, so Newton's first law is a statement about when the force is zero. Newton's second law is a statement about when the force is not zero. When you have a net force acting on an object, the object accelerates, and that's the acceleration. Units for accelerations are meters per second square, units for mass are kilograms, and this combination of units is called a Newton. Okay. Now this is a vector equation, so in 3 dimensions this is really 3 equations. The x component of this vector is equal to x component of that vector, y component is equal to y component, and z component is equal to z component. And that's what we are showing here. So the x component of the force is equal to mass times x component of the acceleration, and so on. And now here's another thing about this equation. The x component of the acceleration is not affected by y and z component of the forces. So anyway, motion along an axis is independent of the motion along the other axes. Okay, so that's Newton's second law. Newton's third law says the following: whenever two objects interact, each exerts a force on the other, and the force exerted by one on the other is equal to the magnitude and opposite in direction to the other force. So if this object exerts a force on the crate, which is given by that, the crate exerts an equal and opposite force on the book, which is in that direction. All right, so, and you often hear this as action and reaction are equal and opposite. The thing to notice is the two forces are acting on two different objects. So those are the Newton's laws. That was just a review of the laws. Now we're going to apply these laws in various situations. Okay, so here's our first application. So here's a traffic light hanging from these two ropes. And you can see that you can think of that knot, and that knot is at rest. So Newton's second law says net force equal to mass times acceleration. And since the acceleration of that knot is zero, the net force acting on it must be zero. And this diagram shows you the three forces acting on the knot. The tension in that string, given by that. The tension in this string, given by that. And the weight hanging, So these three forces must add up to zero. Okay. Now we'll do algebra with the forces, so let's break them down into components. So the tension T2, there's the x component and y component of the tension. Tension T1, here's the x and y components. And for the weight, it only has y components. And since in this situation they need to add up to zero, what we can easily see is these two y components should balance the weight, and these two x components should cancel each other. Okay. So we've applied Newton's second law to this situation. Okay, and given these two equations, we can calculate two of the three unknowns. Two unknowns in this problem. Any two unknowns. All right. Here's a problem here's a situation where the acceleration is not zero. So here the acceleration of the object is not zero. So here's a barge being pushed by two tugboats, and the barge is accelerating in that direction. Yeah. So let's see all the forces act on the barge. There's this force F1 due to this guy, force F2 due to this guy, and here's a drag force from the water. So here's the third drag force. And the sum of these three forces is, there is the net force. The net force is equal to the force F1 plus F2 plus the drag force. And that's the net force. And that should equal the mass of the barge times its acceleration, which is that. Okay, so here's a Newton's second law applied to an object that is accelerating. These are the three forces acting on the barge. The barge is denoted by a point, and so on. Here's an elevator problem. So here's an elevator. There's the tension in the elevator. That's the weight. So we'll simplify this busy diagram. So let's say here's the elevator, tension, mg. M is the mass of the elevator and passengers and all. And if the elevator is accelerating that way, we'll choose that as a positive direction, and we'll write everything in terms of positive quantities. T minus mg equal to A. And if the elevator is accelerating in this direction, we'll write as mg minus T equal to M times A, all in terms of positive quantities. Okay. So if the elevator is accelerating upwards, you can see that tension is greater than the weight. And if the elevator is accelerating downwards, the weight of the elevator is greater than the tension. Okay. Now you can have acceleration upward while the elevator is starting to go up and accelerating up, or it can the acceleration can be up while the elevator is coming down and slowing down. And then this acceleration can be upward. But anyway, when the acceleration is upward, that's when the tension is the greatest. Okay. Here are two objects attached by a string going over a massless, frictionless pulley. And when the pulley is massless and frictionless, the tension on the two sides, on either sides in the string are equal. When the pulley mass is non-negligible, the tensions will be different, but we won't consider that situation now. All right, so since the two objects are attached, the magnitude of their acceleration will be the same. Since the direction is different, we are denoting acceleration as A1 and A2. All right, so the magnitude of these accelerations will be the same, and depending on whether you have friction or not, you'll write the equations of motion of each object. For instance, in this case, for this object, the forces acting on this object are the tension and the weight of the object and the normal force. There's no friction force. If there was a friction force, it would be acting in that direction. For this object, the only two forces acting are the weight of the object and the tension. Okay, so again, we'd apply Newton's second law to the motion of each of those objects. Here's an Atwood's machine. Yeah. Here's a device, again, we'll consider massless, frictionless pulleys. Here's a device depending on the masses. What you can do is you can, so if M2 is heavier than M1, the object will accelerate downwards for M2 greater than M1. And you can adjust the masses so that this acceleration can be anywhere from minus g to g. So here is A given in terms of the masses times g, and A can range from minus g to g. Okay, so what we mean by that is the following. So let's say if m1 were 0, then there's no counterweight, and this would fall down and with an acceleration of g. So if m1 were 0, these two terms would be 0. m2 divided by m2 would be 1, and a would be equal to g. A would be equal to g. And if m2 is equal to m1, if m2 equal to m1, a is 0. These objects will not accelerate. You can get them going at constant velocity, but they would not accelerate. So we got g 0, and minus g happens. Now if m2 is 0, this would be 0, and m1, this would give you minus 1. So that is, it's accelerating upward at g. That is, this guy is going down at g. Anyway, so here's a device where you can adjust the magnitude of these objects to be anywhere, the acceleration of the acceleration to be anywhere from minus g to g. All right, so that's Atwood's machine. All right, let's pause here.